Okay, hello everyone, welcome to the RCNP course. At this part, we're going to introduce the DLDP principle. And for the DLDP, firstly, let's take an overview of it. DLDP, which stands for Data Link Detection Protocol, it uses the RCNP to detect the reachability of the peer device, providing a detection mechanism on Ethernet links. If the detection fails, the interface protocol status is set to done. Then the associated model status changes accordingly, and the interface is rapidly switched. As you can see in this figure, we have two routers. While between these two routers is the service provider's network. And if we assume that there is some fault occurs to the ISP part, and router A cannot figure out this fault, so the local port is up. Router A will continue forwarding data. And at the same time, router A will send the message to router B to test whether the link is reachable. And since actually from the figure we can find there is fault occurs to the ISP networks, so there will not be a response. So after a period, router A will send another message. Why is not the test packet back? Send one more. So it's asking the peer for another test packet response, but there's no response actually. Since the test packet is still not back, so the link is unreachable, and we will shut down the interface. So from here, we can know that actually router A can fix the default route to the outbound interface. Next up is the interconnect interface to router B. An exception on ISP network does not invalidate the route. And DLDP is used to detect the status of a link between router A and B and cross the ISP devices. The test connectivity of peer address. When DLDP detects an exception, the interface status is set to protocol done, and the default route related to the interface disappears from the routing table. And once the route disappears from the routing table, actually, after receiving a packet, if we have a backup route, we will send the packet through the backup route. If there's no backup route, it will be unreachable. Okay, this is the overview of DLDP. And the next is the work process. At the initialization pass, when DLDP is enabled on the interface, it will enter the initialization status and will send an ARP request to obtain the MAC address of the peer. If no MAC address is obtained, DLDP keeps in initialization pass. After the peer MAC address is obtained, here you can see the status will switch to success status. Here you should know that as the wide area network interface encapsulation protocol such as PPP or firm relay or E1, feature link detection mechanism themselves, one interface does not support DLDP. Okay. So this is the application scenario of this protocol. And once the status switch to success, let's see, in this status, DLDP link detection request package can be sent to test connectivity. If a DLDP response packet is received, interface is marked as up. If no response packet is received, request package will be sent continuously till the maximum times of detections. And then the link is marked as failed, and DLDP turns to initialization status. Okay, and the last is the deletion status. In this status, configuration is cancelled and interface status is not analyzed by the link detection function. The interface status is the same as the physical channel status. And if the DLDP configuration of an interface is deleted in any status, the DLDP enters the deletion status. So the switching between different status in DLDP is like this. Let's see a figure, right? Okay. First is the deletion status, right? When the DLDP is disabled on an interface, and once it's enabled, you can see here, once the DLDP is enabled on an interface, it will enter the initialization status. And if in the initialization status we didn't obtain the MAC address of peer, it will remain in the initialization. But once we once we obtain the peer MAC address, we will enter the success status. At the success status, if no detection response packet is received till timeout, we will switch back to initialization. But when a detection packet is sent and the response packet is received, we will enter the up status. Okay, so when everything works properly, the stable status is up. Okay, this is about the working principle of DLDP. And then let's see the configuration of DLDP. Here is a case, and it shows us actually some problems we could face when we use DLDP. You can see here, when an external network line is connected to a PC of a customer, the ping test succeeds. So from here, you know that if the ping test succeeds, means the connectivity is okay, right? However, when the link is connected to a router configured with DLDP, the network connection is unstable. So here you should think about it. If we use a PC, the connectivity is proper. But if we use a router which is running DLDP, connection is unstable. So what's our problem? Later we will see it. Now, when the should log command is run on the device, the following log is displayed frequently. So you can see the log is showing here. It tells us that the DLDP state changed to down. It caused that the interface state has been switched to down. So from here, we can figure out the problem why the connection is unstable is that the DLDP turns down the interface. But why? Why does DLDP turns down the interface? Let's see, the analyze here. The device log indicates that the interface is protocol down because of DLDP failure, causing unstable network connection for internet users. The ping test success on PC indicates that the line is normal. However, default interval of ping test on a PC is 1 second, while the DLDP detection interval configured on a router can be less than 1 second. So from the analyze, we can find that the connection is normal. The reason why it's unstable is that the interval of DLDP detection is too short, or is shorter than the delay that we receive the response from the peer. So it causes that DLDP will turn down this interface because of the timeout, right? So it's used as the possible cause here. According to the analyze, possible cause is that the peer device or ISP line limits the RCNP packet rate. And to solve this problem, let's see the solution. We can enlarge the DLDP detection interval on the device, or confirm and eliminate the ICMP packet rate limits on the ISP and peer device. Okay, this is about DLDP case and the analyze. Next, let's see the configuration commands. Run the following command on the interface to be connected. Pay attention here. This command is used on the interface. Okay, so we should enter the interface configuration view and then use this command. DLDP, the first part is destination IP, and next hop IP. This part or this field is optional, and then interval by the interval time. Retry y means the number of the time we could retry. Resume z represents that the recovery threshold of the link. that is the number of consecutive DLDP response packets received before the link recovers from the down status to up. Okay, so you can see a configuration example here. DLDP 192.168.1.1. This is the destination IP. Interval is 100. Resume is 2. It means that send an RCNP equal every 1 second to test the connectivity of 192.168.1.1. Okay. This is about the configuration command. It's quite easy to understand. So after knowing the commands, next let's see the application scenario. You can see here, access router of a financial branch, router 1, is connected in uplink direction to different ISP and is planned to communicate with router 2 by using floating static routes. ISP A is used at the active link. ISP is a standby link. When ISP A is unreachable, ISP B is switched to. So in other words, from router 1 to router 2, we have 2 paths, ISP A and ISP B. What we like is that ISP A is the active link, ISP B is a backup link. So when everything is normal, all the traffic will go through ISP A, but when ISP A is faulty, we should detect the faults, or we should detect the loss of connection on the path, which is through ISP A, and then we should switch to another path immediately. Okay. Next, let's see the static route switching configuration. Interface Gigabit Ethernet 00 DLDP 10.1.1.2, which is the destination IP, interval 100. By using this command, we can configure the connectivity test from G00 to the peer address once every 1 second. And on the other interface, the configuration is similar, right? DLDP 30.1.1.1, 20.1.1.2, interval 100. So configure the connectivity test from G01 to the peer address once every second. And 30.1.1.1 is not directly connected, so configure the next hop, which is 20.1.1.2. Okay, and since we want to test the connectivity, so we should have routes to the destination first. So here we are configuring the default floating routes. Floating route means to the same destination we have 2 paths, and for one of the paths we change the preference value of it, so it can be a backup route, right? Okay. After that, let's see the verification. After we finish the configuration by using the command show DLDP, you can see for these 2 interfaces, the destination is established and the state of both sessions is up, right? And we can test the switching. To test the switching, we can see when the active link is normal in the IP routing table, we can see the route here, right? We can see the route here, which is via 10.1.1.2. While when the peer port is done, we can see if the service are switched or not. So show IP routes. You can see here we have switched to the another path because it's via 20.1.1.2, which is different from 10.1.1.2, right? And at this time, when you use command show DLDP, you can see one of these sessions state is done now. Of course, there is some fault, of course. Right? We can, for example, manually shut down one of the interface. So about this part, you can see a summary. DLDP link detection is especially applicable to scenarios of interconnection across ISP devices and can prevent rapid data switching failure caused by an ISP line fault. Okay, about the DLDP, let's see some questions. First, a customer wants a router interface to send one DLDP probe packet every second for link detection. So the commands, which is correct, let's see it. DLDP 1.1.1.1 interval 1, interval 10, interval 100, interval 1000. So which of the following commands you think is correct? As we have seen, is C, C. And the next, to ensure that services can be switched over as soon as possible and shorten the fork time, the DLDP detection technology is configured on the outgoing interface of the router. During daily operation and maintenance, the device frequently displays DLDP up or down flapping logs. So possible causes, let's see it. A, quality of the ISP line is poor and there are packet loss and large delay. B, the ISP transmission device has configured the RCNP rate limiting function. C, the peer device of a router is configured with RCNP rate limiting. D, the interval parameter is too large in the DLDP configuration. Here we choose A, B, and C because obviously choose D. If the interval is too large, it will not cause, right? It will not cause the frequent flapping. Only when the parameter of the interval is too small, it will cause this problem. So here we choose A, B, and C. Okay, so that's all for this part. Thanks for your listening.